I'm talking about how machine learning works, giving you a simple visual example that you can follow, explaining different trade-offs and things that affect our prediction results. A short introduction to deep learning and convolutional neural networks. Stay tuned.
3 separate devices. This is one device.
Associate with people who are better than yourself and I'm going to make them an offer again.
Hey everybody, I'm Sam and this is NT-Verso. You're watching part 2 of my series of understanding machine learning, and today we're gonna look at a simple example of linear regression, which is basically the simplest machine learning algorithm of how it works, what are the different trade-offs that can affect if your system is actually learning or not, or if it actually gives you good predictions. A little reminder of what we said in the last video is what's the difference between conventional software and artificial intelligence systems which are using machine learning? Well, in conventional software, everything is pre-programmed, right? So all the states of your software or program need to be pre-programmed. So depending on the input data or some kind of internal results and computation, it has to know where it needs to go. And obviously that becomes a problem when we have systems where there are too many arguments, features, or just simple said inputs. For example, in classification of images or even in a simple search, right? Because there are a lot of different words in a lot of different languages, in a lot of different combinations, and then in every word there could be some kind of mistakes and so on and so on. So the combinations are just incredibly big number. That's why we are using machine learning, and they are very good in exactly classification, for example, in images, sound, facial recognition, in your cameras. And how do they do it? Well, the most advanced machine learning algorithms now are called neural networks, because they're trying to mimic the way our brain and neural system works. We can look at every neuron. It's just some kind of filter that filters the signal coming in, removing all the data that it believes it is not meaningful, and then enhancing the data patterns that actually give us information about what we see, what we hear, what we touch, and so on. So it is the same thing with our neural networks. And today I'm going to show you an example which basically represents only a single neuron. And as we said, neurons are just filters. In our example, our neuron will be comprised of just 2 weights. In every neuron there are weights, and the weights tell us, based on the results that we have shown our algorithm previously, how important every feature that we input in our algorithm is for actually classifying what the prediction output should be. What we do is basically we have a bunch of input numbers, our x value, and we multiply it by our weight, and it gives us a result. For example, it's 2, and then we have a training result of 4. Then our weight will be 2, because 2 multiplied by 2 is 4. And then we present it a new data that it hasn't seen, so it's 3, the weight is 2, so output will be 6. And obviously that's the most simple example that I can show you, but I hope you get the idea. So let's get into our little script here, and I've shown it into our last video. Basically here it's in Python. It's using package called NumPy, and I'll probably do another video explaining more about that and how you can build your own machine learning algorithms, artificial intelligence systems, and a lot of cool stuff. But let's stick to the basics now. So what we have here is our function, right? This is how our input maps to our output. Our input is our x, because I'll always keep the n to be stable or the same value, so it's just a constant. My variable will be x. And then obviously I have an output, right, which is what I return, which I'll call the label or our y, our result. So here I construct my input variable values, which is my x, and here I have 200 points between -1 and 0. That is my training set. So I'll train my machine learning algorithm on values between -1 and 0. Here is my prediction input data set. So those are the real values which I will give to my machine learning algorithm, and I expect it to give me proper results. Here I construct my labels. So again, that's for training. As you see, that's just the function, and added some noise on my data value. So I input my x's and I get my y's. Here I've done the same thing for my prediction input interval, and I do that just because we can see if our predictions are actually the same as the real values we should be getting. If that's true, then our algorithm and warning is working. If it's not, then it's not working and we need to probably do something. Here I construct my design matrix, which is comprised of the features of the input. So it's very important to make a difference between the input value of your variable and your features. The input value is just values between -1 and 0. So for example, it could be 0, right? That's my x. But my feature matrix is features that tell us information about my input. And for example, here, design matrix, my features are just 1, right? It's just a 1. And then the x itself. So for example, for my input of 0, it will be just 1, 0. So it will just be a vector of two values, 1 and 0. Here I construct my design matrix for my real data, or the interval that I want predictions on. And again, it's just comprised of ones and the value itself. So here it will be between -1 and 1, and here it's just 1, 1, 1, 1, 1 always. Here is my training. So what is the training? I multiply a dot product of my two matrices. This is my design matrix, which I constructed here, and these are my labels or my actual training results. So as you see, my weights are my filter, my inputs are my feature, my design matrix, and then I have some kind of output. So if we want to map it to that one, for example, this is just this neuron where I have my input features in and then some kind of output going out. And also that is called supervised training, because I actually give it labels. I actually give it the real values which I expect it to get, and then I expect it to some kind of recognize what the function itself is. At the end, that's the idea. Obviously it won't be perfect, but I want it to somehow estimate it, and this estimation is actually held into the weights themselves. Here I make my prediction. How do I make it? I just multiply my weights by my design matrix. And here, as I said, that this is my design matrix, and I took the Moore-Penrose inverse, and you can read a bit about it. Basically what it does, it guarantees us that it gives us the ultimate weights that gives us the smallest errors from our input data. And those errors actually called residuals in machine learning. So we want the smallest residuals. And here I have just plotted my results. So with red, you can see my training data. Those are the actual labels or the true results that I get with some noise. With yellow are the true results for my real data prediction interval, which I expect to get. And with blue line, you can see my prediction or the prediction of my machine learning algorithm. As you can see here, it's very good. In here, it's actually generalized, it catches the trend, and the prediction itself is pretty good. So what could go wrong? Here I have almost the same thing. The only thing I have changed is my n. So here in the previous example was 1 always, and now it's 2. And what that does in our function is it makes it have a curve. Here we have again our intervals of inputs and prediction. We have our design matrix. We have our weights. And again, those are labels. Those are our actual true values that we expect. And this is our prediction. And as you can see, things are not looking well at all. So our prediction cannot catch the trend. So why does that happen? In machine learning, there is always a trade-off between variance and bias. What variance means is how well our algorithm maps to our training data. And that's obviously very important because in order for the algorithm to catch the trend, and obviously the trend here is that there is a curve, right? And as you can see, our algorithm doesn't catch the trend of the curve, so it doesn't catch the pattern. What that means is it doesn't have enough information. And as we can remember, our feature matrix is comprised only of ones and the X itself. But what that results in is a straight line. So in order to improve variance, or in order to make our algorithm understand better our input data, we need more feature information. So we need to actually understand and know more about our input. And what I change here is when I construct my design matrix, I have the ones here again. I have my X, but also I have added a third feature, which is X on the power of 2. So that's just X squared. And what that is, it gives more information to our algorithm. And as you can see, it is able to catch the trend. And then on our unseen data, here is our unseen data between 0 and 1, it has almost perfect prediction. So here it is very important to understand that features are very important. Obviously, in a real life situation, in something like this, here we have 5 features. But if we have images, we have 1,000 features or 10,000 features, because we actually need to have enough information for our input so our algorithm can actually extract the patterns from it. I hope this gives you an insight about what's happening. And here I have almost the same thing. So what I have changed here is I have trained it on values between -1 and 0 for input. Here I have trained it on values from -0.5 to 0.5, where it can actually catch the actual curve on its bottom, I could say that. And as you can see here, it's fitted even better on the bottom, but then at the end, it's not fitted as well. So obviously, another thing that's very important is your interval of data actually covering the most important points of inflection that gives us the biggest information? Because if I have trained it only on values from here to here, that's almost a straight line. So it carries no information at all about the curve. So that's why we try. You hear that, artificial intelligence needs a lot of input data, millions of photos and so on. And that's why data is so important, because the more data we have, the better we can fit our model to represent it. The more information we can extract, and then obviously our predictions will be better. So one thing is we need to have more features, but another thing is we have to have the most meaningful data possible. And then I want to talk to you a bit about the trade-off, right? So I said there is a variance, which is how well the algorithm fits to seen data, but there is bias, which represents how well the algorithm generalizes. So how well does it fit to unseen data. And obviously that's very important because, theoretically, if we could have all possible combinations of data, we could fit it perfectly, right? But as we know, that's impossible. So idea is we want to fit it well to the seen data so we can actually catch the different patterns, but then we want to make it general. So on unseen data, it again predicts well, because at the end that's the point. Whatever the data is, we have a good prediction. What happens here is we have the same design matrix. So here we have three features, which are ones, x, and then x squared. But what happens here is on our training data, we have a trend, a very smooth curve. And then the curve kind of doesn't happen exactly as our algorithm picks it up, because obviously there is noise. Our algorithm model, you'll see a lot of the word model in machine learning. Model means our weighting of the features that we believe pick up the patterns in data. So our model fits quite well on seen data, but then it doesn't generalize. Why do you think is that? Well, that is because we have three features. So what we have done is we have fitted it too perfectly to seen data, but then in a point where, the data doesn't follow exactly the same trend as the seen data, we can't make a good prediction. So what we can do about that is, instead of fitting it too well, we introduce bias. And obviously there are different ways about that, but in our very, very simple structure, what I do is I just remove the third feature. So I'm back to just ones and x's. And as you can see, what happens is it doesn't fit as well to the seen data, right? But it fits much better to unseen data or to general data. And if you think I cheat somehow, you can see that those are the same values, from 0 to 2, and from almost 0 to around 1. And here you can see it from 0 to 2, from almost 0 up to 1. So bias, and there is a lot of maths behind it. We probably will go much more in depth in next episodes of the series, but the idea is the bias makes it harder for our model to fit too well to seen data, but that hopefully makes it much more general, so we can actually predict much better to unseen data. I would like to finish off with just a small introduction to deep learning, deep mind, the cool stuff that, most of the headlines are, because what I'm talking about, very, very simple examples, which hopefully will give you understanding of how machine learning works. But for deep learning and deep mind, and we'll go much more in that later, there is a lot of cool stuff. So as I said, what I just explained now happens just one neuron. And as you can see here, we have a lot of different neurons, and those are called layers. And here, when a layer is between input and output, it's called a hidden layer. The idea behind that is, obviously, the more layers you have, and remember that, so every neuron has different weights, but every layer has the same features, but another layer has different features. What that gives us, it can pick up different patterns from the same data, from the different neurons. It can give us even more insight on patterns that we couldn't pick up from the features we had before, which means that we can fit it better for different patterns, which gives us, obviously with a lot of layers, much more possibility of fitting it perfectly to seen and unseen data. That makes the trade-off between variance and bias, I guess, easier to do, but obviously we have a lot of more stuff that we can go through. And if you think about, it's the same thing with our own brains, because in our brains we have billions of neurons, and from our eyes, the data to go to our brains, it goes through possibly millions or billions of neurons, which each apply some kind of filters. And obviously that's why, our brains are so good at what they're doing, even though that for the most part we don't even realize it. And here you can see a quick example, which I won't get into depth, of convolutional neural networks. So convolutional neural networks are a type of deep learning, or as called deep neural networks. And why they're deep? Because they have a lot of layers, right? So a shallow is just, one layer or two layers. Deep is when you have a lot of layers, which is kind of logical. What are they good in? Well, they're very good in, as I said, image classification and a lot of different things that pick up patterns, because with them we can actually use unsupervised learning. So how it works is, here you have a first pass which is called feature learning. So through those layers, imagine that all of those are layers with neurons. Here you have much more possibility through different convolutional and ReLU layers to actually pick up features. In our example, we actually make the features, right? We made a matrix of 1s, x's, and x squared. Here you let the machine learning algorithm itself pick up the features that it thinks better represent the data. We don't only train our weights, we also train our features. And when we train our features, we can actually get the trade-off of variance and bias much better balanced, and obviously get much more insight into the data. And I'll be explaining more about that in my next video. I hope you enjoyed this video. I hope it was good for you. You found it interesting, and ask me any questions you would like to know. Stay tuned to NT Versal.